What if the next version of the internet is not defined by speed, but trust? What if the biggest upgrade isn't the data moves faster, but that for certain kinds of communication you can tell if anyone tried to touch it at all? That is the promise behind something people have talked about for years in vague, futuristic language, the quantum internet. And for a long time, that phrase sounded like science fiction, like branding, like one more flashy idea from a field that makes a lot of promises. But now, it doesn't. Because pieces of it are no longer hypothetical. In New York, researchers are turning existing telecom fiber into a live quantum network testbed. Other teams are working on longer-lived entanglement, better repeater designs, and more scalable quantum communication hardware. The quantum internet is still early, very early, but it is no longer just a concept on a whiteboard. And that matters, because the quantum internet is not just the regular internet with better encryption. It is a fundamentally different kind of network built around a fundamentally different physical resource. The internet we use today moves classical information, bits, packets, copies, signals, files. That's one of the reasons the modern internet works so well. Quantum information is different. Unknown quantum states cannot, in general, be copied perfectly. And in many quantum communication protocols, trying to observe the signal changes it. That does not make every practical quantum system automatically unhackable, but it does create a radically different security model from ordinary networking. And that's why the first major application people talk about is quantum key distribution, or QKD. QKD is not about sending your whole message through mysterious quantum particles. It's about establishing a shared secret key using quantum signals while checking whether the transmission appears to have been disturbed. If the statistics look wrong, the two sides know something went wrong, and they can throw the key away. That's the appeal. In principle, it gives you a form of security rooted in physics, not just in the assumed difficulty of a math problem. Now, that doesn't mean practical QKD systems are perfect. Real systems still have engineering limits, implementation flaws, and side-channel risks. And that's important because this topic gets oversold all the time. But the basic idea is still profound. You're no longer relying only on computation to protect the exchange. You're using the behavior of nature itself as part of the security model. And that brings us to a key distinction that often gets blurred. QKD is not the full quantum internet. It's more like one early layer. Think about the early classical internet. First came basic links, then routing, then interoperability, then larger networks, then applications built on top of all of that infrastructure. The quantum internet looks similar in spirit. At the earliest stage, you have point-to-point quantum links and metro-scale QKD systems. At the next stage, you want quantum repeaters and quantum memories that can extend entanglement over much longer distances. And at the far end of the roadmap, you get a true network of quantum devices, secure links, distributed sensing, and possibly quantum computers that can share entanglement across distance instead of operating like isolated islands. That middle stage is where things get brutally hard, because photons in fiber don't behave kindly forever. The farther you send them, the more you lose. In ordinary communication, that problem is solved with repeaters that read the signal, regenerate it, and send it onward. But in a quantum network, reading the signal can destroy the very state you were trying to preserve. So a quantum repeater has to do something much stranger. It has to create entanglement in segments, hold fragile quantum states in memory, and then stitch longer links together through processes like entanglement swapping. That is one of the central engineering challenges of the entire field, and this is exactly why the recent news matters. One of the most concrete real-world stories is the New York effort. Researchers and institutions in New York are working to turn existing telecom fiber into a quantum testbed with the goal of moving from today's entangled distribution systems towards repeater-based quantum networking. That does not mean New York already has a full quantum internet. It does not. But it does mean the field is moving out of the lab and into real infrastructure. And that is a huge shift. Because once you leave the lab, everything gets uglier. Temperature changes, fiber drifts, timing gets messy, hardware ages. Real networks are noisy, inconvenient, and full of compromise. So every time researchers prove that quantum networking can survive more realistic conditions, the story changes. The question stops being, is this concept real, and starts becoming, how far can this be engineered? That is a much more interesting question, and it is also a much more serious one. Because the moment something becomes an engineering problem, progress tends to stop looking like magic and start looking like momentum. That is also why other recent developments matter, even if they sound less flashy. Researchers have been reporting progress on long-lived remote entanglement aimed at scalable repeaters. Other teams are building more scalable quantum communication architectures using integrated photonics. And there have also been demonstrations of distributed quantum computing across optical links, where separate quantum modules are connected and work together. None of that means the finished quantum internet is here, but it does mean the pieces are getting more real, more modular, and more network-like. And that changes how we should think about this topic. Because if you think the quantum internet is only about unhackable communication, you're missing the bigger story. A mature quantum network could support at least 3 broad classes of applications. First, secure communication, especially key exchange. Second, distributed sensing, where remote devices used shared quantum resources to measure the world more precisely. And third, distributed quantum computing, where separate quantum processors cooperate through shared entanglement instead of acting like isolated machines. That third category is especially important because the future of quantum computing may not be one giant machine in one giant room. It may be modular, it may be networked, it may involve separate quantum systems linked together through photonic connections, sharing resources across distance. If that happens, then the quantum internet is not just a side project to quantum computing. It becomes part of the architecture of quantum computing itself. And that is a very different story than the one most people think they're hearing. Most people hear quantum internet and imagine a more secure version of today's web. But the deeper idea is bigger than that. The deeper idea is that we may eventually build networks that don't just move classical data around faster or more safely. We may build networks that distribute quantum resources themselves. And once you do that, whole new categories of systems become possible. Now, the honest version of where we are today is this. The quantum internet is real enough to matter and early enough to misunderstand. If someone tells you it's already here in the same sense that the regular internet is, that's wrong. If someone tells you it's all hype and nothing exists beyond theory, that's also wrong. The truth is more interesting. We now have working metro-scale testbeds, we have active infrastructure projects, we have better repeater building blocks, we have more scalable communication hardware, and we have early demonstrations of distributed quantum processing. But we also still have major unresolved challenges in distance, memory lifetime, loss, cost, interoperability, and practical security. In other words, we're in the awkward middle. Not at the beginning, not at the end. At the point where a technology stops being pure theory and starts fighting with reality. And that's usually the phase that matters most, because this is where you find out whether an idea is just beautiful in principle or buildable in practice. That's the phase quantum networking is entering now, and that's why you should care before it becomes mainstream. Because the technologies that matter most often arrive in stages. First, they sound impossible. Then they become lab curiosities. Then they become fragile demos. And then, almost quietly, engineers start forcing them into the real world, where the physics has to survive contact with budgets, standards, weather, cables, and other people's equipment. That's where the quantum internet is now. Not finished, not fake.
Not magic, an engineering project. And engineering projects have a way of sneaking up on the world. So, if you want the cleanest possible takeaway, it is this. The regular internet was built to move copies of classical information. The quantum internet is being built to distribute quantum states and entanglement across distance. That sounds like a technical distinction, but it could eventually reshape security, sensing, and even the architecture of future computers. Not because it breaks relativity, not because it lets us send messages instantly, and not because it is finished, but because for the first time we are beginning to build networks around the actual rules of quantum physics, instead of just using physics to push classical bits around. And that is why the quantum internet is no longer just a futuristic phrase. It is becoming a real engineering effort. And once something becomes a real engineering effort, you should start paying attention. If you found this useful, a like and subscribe helps us keep making more of these videos. Thanks for watching.